So this iris data has 150 observations and there are 5 variables. First 4 variables are numeric and the last one is a factor variable which has 3 different levels. If you look at the summary of each of these variables, we notice that the variables have different ranges and different values. For example, the minimum is 4.3 here, whereas for sepal width it is 2, and in this case it is 1 and 0.1 here. So later on we'll see that whenever we have like different scales for different variables, it is a good idea to normalize the data so that one variable does not overshadow all other variables. And for the factor variable species, we see that each of the levels have equal data points, 50 each. For repeatability, we'll set the seed at a particular number. I am using 111, but it can be any other number. So we'll take a sample of size 2. So I'm going to use a split of 80-20. So 80% for the training data and 20% for testing data. So training data set has 120 observations and testing data set has 30 observations. So we are going to make use of library called psych, and if this package is not installed, so we need to go to packages and install the package. So I want to see the correlations among independent variables, and for that I'm going to use pairs.panels, and we'll do this plot for the training data, all rows, comma, and we'll not use the 5th variable because that's a factor variable. Gap between scatter plots, I want to keep it as 0. And then for each of the species, we can color them to see what difference we have. We can use bg equals. And we can specify that this is in training data and the variable we want to have colors for is species. We can also say PCH equals 21. So what kind of symbol we want. So this is the plot that we get for the 4 variables. Lower triangle gives a scatter plot and the 3 species are color coded, and upper triangle you can see also gives correlation coefficient. So looking at the scatter plot, we can see that the correlation is highest between petal length and petal width. So you can see this scatter plot here, and correlation coefficient that lies between -1 and +1. So in this case this is 0.97. You can see that these 2 variables are positively correlated and the correlation is quite high, very close to +1. On the other hand, we see the lowest value, which is almost close to 0, is here. So between sepal.width and sepal.length, the correlation seems to be very low. So in 3 cases, correlations are more than 0.8. This number refers to sepal length versus petal length, and this is the corresponding scatter plot, and coefficient is 0.86, which is quite high. Similarly, this is between sepal length and petal width, this one here. So that correlation also is very high. So when we are developing predictive models and when correlation among independent variables are high, that gives rise to multicollinearity problems. And the estimate for the models that we get are very unstable, or predictions are not going to be accurate. So one way we can handle this is using principal component analysis. We are going to store results in PC, principal components, and the function we use is called PRCOMP, PR for principal, COMP for component. So this performs a principal component analysis on the given data matrix and returns the results as an object of class PR comp. So we'll make use of training data. After comma, I'm going to put -5 because we don't want fifth variable. So principal component analysis is done only on the independent variables. And also we want to make use of center. So this will make sure that the variables are converted in such a way that the average becomes 0. And we can also use scale. So this is scale, and then we have to put a dot equals true. So this will make sure that before principal component analysis is done, all the 4 variables are normalized. So now if you want to see what attributes are stored in PC, we can make use of attributes. So we have standard deviation, rotation, center, scale, and so on. For example, if you want to see what do we have in center, we can say PC $center. So this gives us average of each of the 4 variables. If you want to do the calculation, you can do mean, and because this is based on training data, we say training and sepal length. So you can see we get a value of 5.79 as an average of this first variable, and that's what is contained in center. By making use of this center, we have made sure that we calculate average of all the 4 variables. Similarly, if you want to see what is contained in scale, you can say PC $, and scale. If you want to calculate standard deviation of training data and the first variable, you find that we get exactly same value. So basically this scale dot ensures that standard deviation for each variable is calculated. So all these 4 variables are normalized. Now let's print PC. So when we print PC, we get standard deviations and also rotations, which are also called loadings. So because we have 4 variables, we have 4 principal components. So PC1, PC2, PC3, and PC4. So each principal component is a normalized linear combination of original variables which are listed here. So these rotations or loadings are the coefficients of the linear combination of the continuous variables. These numbers that we see for each principal component, so these values are going to lie between -1 and +1. So these values indicates that principal component 1 increases as sepal length, petal length, and petal width increase, whereas as PC1 increases, sepal width decreases because this correlation is negative. So the highest value is for petal length, and the lowest value in terms of correlation is for sepal width. Similarly, if you look at principal component 2, the highest value is 0.91 and it is negative. So that means as PC2 increases, sepal width goes down. So they have negative correlation, and that negative correlation is quite high because this is very close to -1. The other correlations are much lower compared to this one. So this principal component is characterized mainly by sepal width. Next, let's look at summary of PC. So we have these standard deviations, and then we also have proportion of variance. So first principal component alone explains about 73.7% of the variability. So principal component 1 captures majority of the variability, whereas second principal component captures about 22% of the overall variability. So this keeps on going down, and we also have cumulative proportion. You can see by the time we reach second principal component, more than 95% of the total variability is being explained. So by the time we reach principal component 3 or 4, they do not play a very important role in terms of variability. In this case, we can say first two principal components more or less capture majority of the variability. So let's create a scatter plot again using pairs dot panels, and this time we want to create it for the principal components that we calculated, which are stored in X. So we use $ and X. We'll keep this gap as 0, and we'll again color code. So we can see all the possible scatter plots between the four principal components. We also notice that the correlation coefficients are all 0. Since principal components are orthogonal to each other, correlation between them are always 0. So that helps us to get rid of multi-collinearity problem that occurs when we have many variables which are highly correlated. So we had seen that original variables had a correlation of as high as 0.97. But now by making these principal components, which are linear combination of normalized variables, we find that the correlation is now 0. So that will help us to get rid of multi-collinearity problem. So for making a biplot, we need package called DevTools. So let me install this. Similarly, we have to install from GitHub. So you can install ggbiplot by using this line. I'm not running this because I have already installed this. But make sure that before you do that, you have ggplot2 already installed. Once I run this library, so we are ready to use this package. I'm going to store within ggbiplot the principal component that we created, and then I'm going to enter some more attributes. So observation.scale is 1, var.scale, I'm also keeping this at 1. So for this one, we use within the training species variable. We'll also plot ellipse around the data points, so we can say true. And then we also need a circle for the biplot, so we'll say circle equals true. And for the ellipse, we can also specify ellipse probability. So I'm going to start with default value of 0.68 or 68%. So we run this line. So this should be training. Now we add some more layers to this G. So G plus scale underscore color. We are going to use this one, scale color discrete. So name equals within quotes. And then we add one more layer. So G plus to be horizontal, legend position, so we want to keep this at the top of the chart, and then finally we can print the chart. So this is the biplot that we get. So on the x-axis we have first principal component PC1, which explains 73.7% of the overall variability. And then on the y-axis we have second principal component that explains 22.1% of the variability. The species are color coded. So first species is in red, second one is in green, third one is in blue. So this ellipse is made in such a way that it captures 68% of the data. So 68% of the variability or the data is captured by the ellipse. So instead of 68%, if you make it 0.95, then this ellipse is going to become bigger and bigger. So this is going to include more and more data points that are red in color. So within the circle, we also see there are 4 arrows representing each variable in the data set. So those arrows which are closer to each other, for example, petal length and petal width. So these two variables have high correlation between them. So if you recall, between these two variables, correlation coefficient was about 0.97, which was very high. And similarly, this variable also has higher correlation with these two variables. But this line, which is for sepal width, is far away from these three. That means correlation between any of these variables and this variable is on the lower side. So they are not really highly correlated. Now, if you look at first principal component, so in the middle you see 0. To the right side we have positive values, and because first three variables are on the right side, that means correlation between these variables and principal component is positive, whereas this variable is on the negative side. It means that correlation between sepal width and principal component 1 is negative. And this is what we see here. So petal length has the highest value, 0.57. So petal length is the top one, and it reaches the maximum value in terms of principal component 1. Next, high correlation between principal component 1 and the variable is with petal width, 0.56, and that's why this is the second one. Whereas sepal width is negative, so you can see it is on the negative side. Similarly, if you look at second principal component, so you can see all the variables have negative correlation with PC2, and in fact sepal width has the highest value on the negative side. If you look closely, PC2 we have 0 line somewhere here, and you can see all the arrows are below this 0 line. That means all the 4 variables have negative correlation with principal component 2. And sepal width you can see because it goes further down compared to other 3. So this is highly correlated in a negative way with principal component 2. So as principal component 2 increases, sepal width goes down, and it goes down much more than other 3 variables. A point that is far away on the right side, so this point indicates that it has high value for the first principal component, which also means it has high values for petal length, petal width, and sepal length. Similarly, a point which is, let's say, on the left side, so it has low values for PC1, so which also means that it has low values for petal length, petal width, and sepal length. Similarly, if you look at a point related to principal component 2, let's say this one, a high value for principal component 2 automatically means that it will have low values for sepal width, because this is the dominant variable and it has negative correlation. So this biplot is a very important tool in principal component analysis to understand what's going on. So we can predict using predict function. So let's make use of PC and training data, and let's store this in TRG for training. So if you look at TRG, you'll find that we have all the values converted into principal components for all 4 PCs. So for the purpose of our analysis, what we will do is within training, so we convert this into a data frame, but we'll also add 5th column which contains species information. So now if you run this, you have not 4 principal components but also the last column with species. Let's do same thing with testing. So now we have data ready in terms of principal components to develop predictive model, and for that I'm going to use multinomial logistic regression. Because our y variable, which is species, has 3 levels, we do multinomial logistic regression. We need a library nnet, and within the training data set we use relevel. So in this line we are just indicating that our reference value is the first species, which is Setosa. So now we are ready to do multinomial logistic regression. We'll store this in my model. So species as a function of PC1 plus PC2. So we are using only 2 because they have more than 95% of the variability captured. And our data is TRG, training. Very quickly this model converges and we get some solution. If you look at the summary, so it provides the model with intercept and coefficients. So let's store within P predict using my model and our training data, and then let's store within tab this table of P values and TRG $species. So if you want to look at this table, you can run tab. So you can see there were 45 observations with actual classification into first category, and the model also predicts them to be belonging to the first category. So this is correct classification for the first category, and there are 35 correct classification for the second category and 32 for the third one. There are 3 misclassifications. So actually they belong to category 3, but the model predicts them to belong to second category. So this is a misclassification, and another misclassification is here. Actually they belong to second category and model says they should be in category 3. We can calculate misclassification error. So misclassification is about 6.6%. So misclassification error for testing data is about 13.3%.